Zero-carbon homes have been receiving increased attention in recent years as a result of constant concerns about energy supply constraints, decreasing energy resources, increasing energy costs, and the rising impact of greenhouse gases on the Earth. This lecture provides basic information on zero-carbon housing, as well as building innovations such as prefabrication as an example. What is a zero-carbon house? A house is a system of energy and environment, striking a perfect balance between lifestyle needs and the needs of our environment by minimizing and offsetting both embodied and operational energy use. Embodied energy is used to extract materials, manufacture building components, and transport them to the construction site. Moreover, this energy encompasses the construction of a house. On the other hand, operational energy is used to heat, cool, cook, light, and entertain housing occupants in activities of their daily living. Both types of energy use result in carbon dioxide or CO2 emissions that contribute to global warming. Embodied energy could be reduced by applying building innovations such as prefabrication of housing components, which helps mitigate production of material wastes while enhancing efficiency in construction. With regard to the history of housing, prefabrication may be considered as an invention of the 19th century industrialization. It is a way to realize off-site construction of housing where the parts and components or entire units are fabricated in the environmentally controlled factory. After the in-factory assembly, they are transported to the building site where houses are erected eventually. Dwellings built through the prefabrication process are referred to as a prefabricated homes or prefabs simply. This slide shows some typical prefab building systems such as post and beam, panelites, and modular systems. Post and beam systems include the in-factory assembly of vertical and horizontal structural elements made of wood, steel, or even concrete. Panelite systems secure production of walls and floor panels inside the factory, which accounts for nearly 40% of housing components. Panels manufactured inside the factory will be transported to building sites for further on-site assembly. In the modular systems, housing components such as bedroom, living room, dining room, kitchen, bathroom, and so on. These units are manufactured as a set of modules, which account for over 80% of housing elements. After the in-factory assembly, these modules will be transported to building sites for further on-site assembly using a crane in many cases. Higher the in-factory completeness of housing components, the better the product quality. Such industrialized home building process can be carried out rapidly with a minimum of on-site labor effort and under any conditions of weather and season. Accordingly, the use of prefab systems helps reduce or eliminate site nuisances such as bad weather, theft, and vandalism, those that are often inevitable in on-site construction. Particularly, prefabrication contributes to raising the level of reducibility, reusability, and recyclability of building materials. Therefore, it helps reduce the level of embodied energy consumption in the housing delivery. Prior to discussion of zero-carbon housing, operational energy use needs to be reduced to low or zero levels. In essence, zero energy housing falls into two categories: self-sustainable or net. Former type is a stand-alone house whose operational energy relies solely on its own power generation and storage. Therefore, it is disconnected from a commercial grid or uses power from their outside sources. On the other hand, net zero energy housing is a house whose operational energy use becomes net zero over a fixed period of time. Net zero site energy means that the annual balance of operational energy use is based on the grid interaction at the boundary of the building site. Therefore, operational energy delivered to the building from the utility grid is offset by the overall energy fed back into the grid. Net zero source energy is based on the net zero balance of primary energy use. Therefore, transport loss of energy delivered from power plant is taken into consideration. Net zero energy cost is defined based on the economic balance. A house whose energy bill becomes net zero over a fixed period of time is termed net zero utility cost housing, or simply net zero energy cost housing. The notion of net zero energy emissions building can be considered as equivalent to that of buildings whose CO2 emissions derived from their production and operation are estimated to be net zero over a fixed period of time. Therefore, zero carbon homes can fall into this category. Here are some design considerations for net zero energy housing. Before relying on the use of active mechanical solutions, namely renewable energy technologies, such as solar photovoltaic power generation system, solar thermal, ground source heat pump, air source heat pumps, wind turbines, and so on. Passive design solutions should be sought in order to minimize buildings' energy demand. Passive design approaches play as fundamental role in net zero energy housing design. Orientation of building facades, configuration of a house, the choice of color and materials applied to housing definitely affect the thermal characteristics of a house and overall energy efficiency. International Energy Agency, or IEA, Task 40, Annex 52 program developed an energy balance diagram in order to standardize the definition of net zero energy buildings. Their definition is based on the notion of net zero source energy use, which was explained previously. For the demonstration, 9 projects were selected from different countries based on their physical characteristics as well as simulated and monitored energy performance data. According to IEA definition, 3 buildings plotted below the energy balance line are considered to be near net zero energy buildings, while 6 buildings above the border lines are considered as plus energy buildings, whose operational energy excess is used to digest the embodied energy consumed during the production. Housing types can also be defined according to energy usage profile. For example, conventional homes rely on 100% of utility supplied electricity and natural gas. High-performance homes can save 30% to 50% of utility cost over conventional housing, while 60% to 90% of energy costs can be eliminated in near zero energy housing. Zero energy homes can cover virtually all of the domestic energy use. Zero carbon homes surpass the performance of net zero energy house, which export electricity to the grid 20% more than energy used in the house for at least 25 years, thereby offsetting embodied energy used for their production. This lecture further explores how zero energy or zero carbon homes have actually been designed and produced and commercialized by making use of some successful examples selected from Canada, Italy, Japan, and the UK.